For exam 1, we have a handful of equations that we need to know for the exam and identify what equations and how to use those equations, and knowing when to use those equations. And the first two we really can ignore from this list. The first two equations are basically the Arrhenius equation, and they look at the relationship between activation energy, EA, and the rate constant of a reaction, and this is just a rearranged form of that. These equations were covered in Module 13. That being said, I'm not going to ask you any questions based on these equations. The next equation really wasn't any equation that was given in the text, but I provided that to help you find the rate order of a reaction, where N gives us the rate order for the reaction with respect to a certain reactant. And in the case when we would use this equation would be where I give you a data table of multiple experiments. You'd have experiment 1, 2, 3, and you'd have different concentrations, and you'd have different rates in each of those experiments. And we would have to compare those concentrations and the rates from different experiments to find the rate order of that reaction with respect to each species in the reaction. This would be the case where if you observe the concentration doubles, you would expect to see the rate doubling as well for a first order relationship. Or if we doubled the concentration and the rate quadrupled, that would be a second order relationship. And so we would solve these equations, and in class when we solve these equations, right, for a first order reaction, we saw something like 2 to the power of n equaled 2. Well, to solve for n, right, n had to be 1. N had to be a first order reaction. And when it was a second order reaction, we'd see something like 2 raised to the power of what equaled 4. Well, in this case, obviously n had to equal 2 because we have a second order relationship. The next equation we need to know, and we absolutely need to know the next equation, is natural log of concentration at time t, so this is some time in the future, equals negative rate constant times time plus the natural log of my initial concentration. So A0 is my concentration at the start of a reaction. This is the integrated rate law for a first order reaction. Right, so something we need to know is this equation is for first order reactions only, right? And because of this equation, to identify a first order reaction, either they're going to tell us in the question that it's first order, or if they give us some graphical information, right? Natural log of concentration versus time for a first order reaction would be a linear relationship. And the key thing being here that our y-axis is natural log of concentration versus time, linear relationship, first order reaction. In this case, you'll need to know an initial concentration, a rate constant, and time to find the concentration at some point in the future. Or we saw examples of this as well where I gave you initial concentration in the future and then a period of time and asked rate constant, or gave you rate constant and asked for how long would it take. So really you could be able to solve for anything in this equation. And then related to our first order reaction, we also talked about the first order half-life reaction equation as well. And so the half-life for a first order reaction equals 0.693 over K. Again, I would give you one of these and you could solve for the other. I could give you rate constant, we could find half-life. I could give you half-life, we could find the rate constant for that reaction. And there were a couple times where we did questions where you needed both of these equations. We needed the first equation to find rate constant, and then we used half-life equation, plugged in rate constant, and that gave us a half-life of a reaction. The next equation that you definitely need to know is the integrated rate law for a second order reaction. And this equation is 1 over my concentration at time t. So this is my concentration in the future, equals my rate constant times time of the reaction plus 1 over my initial concentration. So A0, again, is the concentration at time 0 of the reaction, right when the reaction starts. Just like for the first order equation, you should be able to, given concentration at the start and at some point in the future and the time that it takes to find rate constant, or if I give you rate constant to find time, or if I give you initial concentration and time and rate constant to find what concentration we have at some point in the future. Remembering the problem that we worked through in class, we solved for 1 over concentration, so to find concentration, the last step in that calculation is to take the inverse. You might know it's a second order reaction if they tell you in the equation or if they give you the data based on a graph, right? We would look for 1 over concentration versus time, and that needs to be a linear relationship if it's a second order reaction. I know both of these graphs are linear, but what's important is what's on the y-axis. If it's natural log of concentration versus time, and it's got a negative slope, that's a first order reaction. If it's 1 over concentration versus time, and it has a positive slope and it's linear, that is a second order reaction. And that sums up the main equations for Module 13. For Module 14, we looked at equilibrium and our equilibrium constants. And we got our equilibrium constant from our reaction coefficients. So for the following reaction of A plus B goes to C and D, right? The exponents in our equilibrium expression simply came from the coefficients in our balanced chemical reactions. So they're always in the form, I should also add, they're always in the form of the concentration of products over the concentration of reactants. But our coefficient of A becomes an exponent A, our coefficient of B becomes an exponent here, and then the same thing for our products, C raised to the power of C and D raised to the power of D. Always concentration of products over the reactants, and remember, we can ignore solids and liquids in these equilibrium expressions. One final thing about nomenclature and the words we're using. This is our equilibrium expression. That's actually just it written out with what do we have, what are the concentrations, what are the exponents. My equilibrium constant is the value from that, so the end result of this calculation. The expression would just be what is it for the reaction, plugging in each reactant and product that I have and the exponents that I have from the reaction. The actual equilibrium constant would be the value of that. So Kc is concentration based on molarity. We'll also see Kp, and that's just based on partial pressure. So if we're given value, so Kc is molarity. Kp is partial pressure in ATM. Same thing, products over reactants. We can also relate Kp to Kc. They can be equal. Kp equals Kc when our change in moles in the reaction is 0. When there are equal number of gas phase moles on both sides of the reaction, my delta N, my change in moles, is 0. So RT raised to the 0 becomes 1. So that means Kp equals Kc when the number of moles on both sides of the equation are equal. In other cases, we might have to find that change in moles to see what's the relationship between Kp and Kc. R is the gas constant, which would be provided, and T is temperature in Kelvin, which would also have to be provided to use this equation to relate Kp to Kc. The last thing we looked at was our reaction quotient Q. Reaction quotient Q is calculated the same way we calculate our equilibrium constant. It's always going to be the concentration of products over reactants. The main difference being that Kc or Kp are equilibrium concentrations only, whereas Q is at any point in the reaction. Q is helpful because Q gives us directionality. So if I have my reaction, my generic reaction going from reactants to products, and I calculate a value of Q if Q is greater than K. We talked about this in class because if we said if Q is greater than K, what that must mean is I have a higher concentration of products. I have a higher concentration of products than I would otherwise have at equilibrium and a smaller concentration of reactants, right? Because a larger number divided by a smaller number, and let me switch pointers because I think that pointer's not the best. This maybe is a little bit better, right? A larger number divided by a smaller number is going to give me a much bigger number. So when Q is greater than K, I have more products than I would expect at equilibrium. That means the reaction went beyond equilibrium. So to return to equilibrium, the reaction will move to the left. The equilibrium will move to the left. The reaction moves left. And the other side of the calculation, let's say I have a value of Q that is less than K. So now, if Q is less than K, still going to put Q over here, I'm going to put K over there. If Q is less than K, what that must mean is that at Q, where I'm calculating Q, I've got a higher concentration of reactants than I'm expecting at equilibrium and a smaller concentration of products than I'm expecting at equilibrium. What that means is I need to increase the concentration of products. To do that, I need to push the reaction farther forward. I need to increase the concentration of products using more of the reactants until Q equals Kc. So when Q is less than K, the reaction is yet to reach equilibrium, and so to reach equilibrium, the reaction will move to the right. So Q is very helpful in giving us the direction of a reaction. And then it's not given here, but obviously if Q equals K, well, then we are at equilibrium. So hopefully that summary helps you kind of think about what to look for when you need to use each of these equations. Because that'll be the biggest challenge for this exam, is just identifying what equation I need and when I need that equation.